Hi, welcome back. Today I'm gonna start a series of videos concerning angle of attack and stall warning computer. I will start today with this angle of attack indicator. This one was manufactured by Teledyne Avionics in Charlottesville, Virginia. Such indicator is normally connected to a stall warning computer. I have one here. This one was manufactured in 1997. The main input of a stall warning computer is an angle of attack sensor. I have one here. There is a heater inside, and this is the differential synchro. The stall depends on the angle of airflow, of course, but it depends also on the position of the flaps. I have here one flap sensor, so this is the synchro actually. I have here a documentation regarding the Boeing 720 and the 727. We can see here on the left the angle of airflow sensor, and we can see that on that system the angle of airflow sensor is directly connected to the flap position sensor, which is also a synchro, and the result is fed to the stall warning module. I have already described several years ago this module. There is a demodulation of the AC signal, a comparator, and this permits to activate the stick shaker. And there is also a detection of the current which flows through the heater here using this current transformer. Okay, quite interesting. We have two electronic boards. Some parts are not populated, so I think that the pointer here is linked to a DC motor, and we can see here you have a feedback potentiometer. It's a wire-wound type. Okay, so we can see here the track of this potentiometer. Okay, so we can see the three wires here connected to the potentiometer. Okay, so we have two other wires here probably for the lighting, and we have also one pair of wires here for the flag. Okay, so we can see that we have several 741 classic op-amp back in the day, and we have here another IC MC3302. So this is a quad op-amp. Okay, so we have a better view on the board. And here we have the connection for the DC motor. Okay, so we can see here a medium power transistor, and we have also three of them here. So here we should have the servo amplifier. There is a tantalum capacitor. There are two trimmers and several op-amps. We have two 741. There is an LM108 here. Okay, and there is another quad op-amp 3302. And we have here an MC1556. This should be another op-amp.
We can see here the main circuit of this indicator. This is the servo control loop. The servo amplifier is here. There is a summing point. The DC motor is here. So this circuit is actually a virtual ground. This node is at mid power supply. So this circuit simulates also a negative resistance, which permits to compensate the resistance of the motor. So this permits a control of the velocity. We will see this circuit in details later. So here we have the feedback potentiometer. So we can see that there is a voltage follower. We can see that the wiper of the feedback potentiometer is not connected to the servo control system here, but it is connected to one terminal of the connector. Okay, so we should provide here a link between terminals D and E. I don't know why they have separated the feedback potentiometer from this voltage follower. And here we have the summing point. So this is the virtual ground. So you can use the input as an inverting amplifier. In that case, the input voltage is positive. We have a voltage limiter, and the difference of these two currents here flows through the feedback resistor, and the output here is fed to the DC motor. VO here is the output of the servo amplifier. The motor is here. We can see here a simplified schematic. The DC motor comprises a back EMF voltage, which is proportional to the velocity of the shaft. RL is the winding resistance of the DC motor, and we have here the current sense resistance. The current sense resistor is made with copper, and this resistor is kept at the same temperature than the DC motor. Okay, so if you suppose first that we have a perfect motor with no load, so therefore the current flowing through the motor is null. Okay, so therefore we can see that the back EMF voltage here appears across this resistor R2. Okay, and the voltage across this resistor is proportional to the input voltage here, which is the output of the servo amplifier. Okay, so therefore the velocity of the shaft is proportional to the input voltage here. If you suppose now that we have a torque applied to the motor, there will be a current flowing through that direction. In that case, the voltage at this point increases and the velocity of the motor decreases, but at the same time, because of this local positive feedback, there will be an increase of the output voltage here. So therefore there is a compensation and the velocity of the motor is constant. Of course, the positive feedback should have lower effect than the global negative feedback here. So this is why this resistor is adjustable. Let's do the calculation of that circuit. In order to reduce the number of variables, I have defined these two ratios, Rs over Rl and R1 over R2. Okay, so this permits to have only two parameters instead of four. The idea is to calculate these two voltages here, the non-inverting input voltage and the inverting input voltage. So first we have for the non-inverting input voltage this equation, it's a simple voltage divider. And for the second voltage, we can use the superposition theorem. Okay, so we have two voltage sources, the input voltage here and this voltage, which is actually the output voltage minus the back EMF voltage here, okay, which is proportional to the velocity. Okay, so this is this voltage. If you consider that this system is stable, these two voltages are identical, and you find this equation. Okay, so at the end you find this very nice equation. That means that the velocity of the motor is function of the output voltage here, Vs plus Vin. So we can see that for a particular case, when alpha equals beta, this term disappears, and you have a velocity proportional to the input voltage here. Okay, it depends also, of course, of the factor k of the motor, and alpha, which is the ratio of these resistors there. So you can see that we need effectively to have a constant ratio Rs over Rl. And this is why the current sense resistor Rs is made with copper, and it is located around the motor in order to have the same temperature. So therefore the ratio Rs over Rl is constant versus temperature. This permits to have an optimum damping at all temperatures.
And we can see that we have a setting here which permits to set the ratio speed over stall speed. Okay, so we can see that we have a pointer here, and we have also this bug here. This bug permits to define two limits actually. On the schematic, there is a second circuit which permits to drive three lamps. Okay, we can see these three outputs here. The lamps should be connected between each output and the ground. And we have three comparators. We can see here a differential amplifier. This differential amplifier is connected between the feedback potentiometer, okay, so which is here. So this is the voltage corresponding to the angle of attack. And the second input is here. It corresponds to this potentiometer. So the difference is fed to this amplifier. The gain of this amplifier depends on the setting here. The gain is activated when this bug here is below 0.5 approximately. Okay, so this is why we have these two internal limits here when the gain is activated. I have connected the input to this potentiometer, and these three lamps are connected to the collector of each transistor here. Okay, so let's turn on the power supply. I am going to activate the lighting also. Okay. Okay, so we can see also the damping of the needle here. So we can see that the speed decreases when the pointer is close to the final position. So this is due to the compensation of the winding resistance of the DC motor. The scale here is normalized. Okay, so normally we should be inside the green area as usual. 1 corresponds to a stall, so we should avoid absolutely the red area here. Okay, so for 0, the input voltage is 4.5 volts approximately. 1 corresponds to a voltage of 18.6 volts. Okay, so one more time. .7 volts for 0.5. That's all for this angle of attack indicator. Thank you for watching and see you next time for another video. Bye bye.